and sharing my screen. Maybe, there we go, sharing my screen. And first thing I'd like to look at are a couple of general announcements that I put in the notes. Today's February 4th. We're going to look at rational exponents, which is kind of going to relate what we did in P2 with exponents to what we've done so far in P3 with radicals. Then we're going to do a little bit of introduction to that next section, P4, which is polynomials. So homework P2 on exponents should be done by the end of the day today. Homework P3 on radicals should be done by Tuesday. Homework P4 on polynomials is due a week from today. There is a quiz 2, that is in My Math Labs. You're going to take it in My Math Labs, but you must submit the work in Blackboard. It has 12 questions. We have about half an hour for it. It involves exponents, but it's got some of that P3 stuff in it, simplifying radicals and rationalizing denominators. Any questions on just the timing and the logistics of all of that?
When did you say that was due again?
That quiz will be available after class today, and it's due by 11:59 Sunday.
Okay, thank you.
Okay, so, I know that that's because of the pandemic, nobody has too many weekend plans, so let's fill it with the fun stuff, math, right? So, before we get started with the rational exponents, I wanted to make sure everybody's all right with everything so far. Does anybody have any questions on anything in any of the homework assignments? Does anybody want me to, I've got My Math Lab open, you guys can all see that. Does anybody want me to look at any problems? Were there any problems that people had concerns with? And before you start answering this run-on sentence of mine, please realize you don't have to wait for class time to get homework questions answered. You can always use that email my instructor. And please, if you did send me something, email my instructor. Give me a gentle nudge to my memory so that I can go over those problems with everybody. Because it's been my experience that if one person in class has a question about something, there's usually more than one person. And so asking question helps you, but it also helps your peers. So that having been said, does anybody want to look at anything from any of the homeworks?
For question 17, for radicals and rational exponents, I was sort of struggling with that.
Okay, let's go ahead and let's look at that one. And while I'm waiting for that to open, for laws, I got you in attendance. Okay, so it asks you to evaluate the expression or state whether or not it's a real number. No, this is question number 1. I have to actually go to question, you had said number 13, right?
17.
17, I'm sorry.
Yeah, that's
fine. You're asked to rationalize the denominator. And this was one of the last things that we were looking at last class. We had said that a radical is in simplest form if the radicand has no perfect square factors, if the radicand is not a fraction, and if I have a fraction, there's no radical in the denominator. So as I look at this one, I've got a radical in the denominator. If I were to change that into a single fraction, I can't reduce it to clear the denominator. So what I have to do is I have to say to myself, what can I multiply the square root of 5 by to get something that's a perfect square underneath that square root? And are you all right if I multiply the square root of 5 by the square root of 5, doing just that multiplication in the denominator? I'd get the square root of 25, which is just 5. And so now I no longer have a radical in the denominator. What you have to remember, though, is when we do this multiplication, we want to make sure that we're only multiplying by 1 because we don't want to change what it equals, just what the fraction looks like. And so if I multiply the denominator by the square root of 5, I have to multiply the numerator by the square root of 5. Numerator and denominator need to be multiplied by the same thing. Multiplying the numerators then, radical 2 times radical 5 is radical 10. And so my simplified answer is the square root of 10 over 5. So let me turn my finger back into mouse, open my, open my keyboard, go down to this toolbar. We want, let's try that again. The square root of 10, and we want to get out of there and put that over 5, and yes, we got it. So yay. Does anybody else do a little happy dance when you get that fantastic, excellent next question? But I'm carrying on. Does that make sense, hon?
Yeah, it does.
Okay. The other type of problem where you have to rationalize the denominator, that's a little bit more involved. Oh, you know what? Let me just scroll through. Are ones where you have 2 terms in the denominator. And is everybody all right if I use that next homework problem as an example of that to kind of just refresh your memories? If I have 2 terms in the denominator, like here I have 2 plus the square root of 13. I can't just multiply by the square root of 13 because there would still be a radical left when I distribute. And that was where we looked at those 2 terms and came up with something that was called the conjugate. And the conjugate of 2 plus the square root of 13 is 2 minus the square root of 13. And so we're going to multiply the denominator by 2 minus the square root of 13. And again, if we multiply the denominator by that, we've got to multiply the numerator by that same thing. This time, let's multiply the numerators out first. Because I'm multiplying 11 by what's in the parentheses, I have to remember to use the distributive property and multiply each addend in the parentheses by that. So 2 times 11 is 22, and 11 times the square root of 13 is, well, just 11 times the square root of 13. Because there's a minus sign in between, that'll be negative. Then in the denominator, what's special about those conjugates is if I multiply A plus B, a sum, by the difference of the same terms, A minus B. Last class we said that always turns out to be the first term squared minus the second term squared. So that product in the denominator is going to give me 2 squared minus the square root of 13 squared. And I have to apologize, I wrote too much down here and didn't leave room for my work. And so that's going to give me, my numerator's still 22 minus 11 radical 13. 2 squared is 4. The square root of 13 squared is 13. So my final answer would be 22 minus 11 times the square root of 13 over 4 minus 13 would be negative 9. And does everybody remember looking at those problems last class where we had to rationalize a denominator that has 2 terms in it? Anything else from the homework that anybody else would like to go over? Is everybody okay if I clear this one?
Yeah, it's fine.
Great. Any other homework questions that people are wondering about? There will be questions like both of those on the quiz where you have to rationalize a denominator. So be careful with them. Do the homework first, I guess. Try to get through that homework first. Anybody want to look at any others? Have I been patient? Did I wait long enough?
Yeah, I'm good.
Okay. All right, then let's go through and let's pick up from where we left off last class. And if I remember correctly, last class we ended with looking at other roots. And with other roots, we said that the nth root of A equals B if A is equal to B to the n. So, for example, if I was looking for the cube root of 125, what I would be doing is I would be saying what number to the third power equals 125, and through trial and error or through your familiarity with your multiplication facts, hopefully everybody recognizes that 125 is like 5 times 25, which would make it 5 to the third. So the cube root of that is 5. And instead, let's say I have something like the fourth root of 32x to the ninth over the fourth root of 2x. Because these are radicals, they'll follow those rules for radical. And so that would be equivalent to, I can change that into a single fraction, the fourth root of 32x to the ninth over 2x. And while neither of those are perfect powers of 4, when I take the quotient, 32 divided by 4 is 16. X to the ninth divided by x is x to the eighth. And I think last class we made note of the fact that 16 is 2 to the fourth. And if I look at x to the eighth, that would be x squared to the fourth. And so we can use our radical rules with these other radicals, with these indices, the little numbers in the check mark of the square root symbol. Is everybody okay with those other roots? Not hearing any questions, that's then the idea, that definition, to say that if the nth root of A equals B, that A is equal to B to the nth power, that allows us to give meaning to a rational exponent, which means that I can have fractions as exponents. And to look at this, let's look at something like the square root of x. If I take the square root of x and square it, that would give me just x. But if I think about my rules for radicals, if I had something like x to the 1/2 power and squared it, well, x to the 1/2 power to the second, when I raise a power to a power, I multiply those exponents. So that would give me x to the 1/2 times 2, which would be x to the first, or just x. So if I take x to the 1/2 and square it, I get x, which leads to the fact that x to the 1/2 behaves just like the square root of x. And so I'm going to say, in general, if I have x to the 1/n, where n is a natural number, that's going to equal the nth root of x. And so, for example, if I wanted to take 81 to the 1/4 power, well, if I look at that fractional exponent, a fractional exponent tells me I'm going to draw get a radical. The denominator becomes the index on the radical. So since I'm looking at the 1/4 power, my index is 4. And the base is the radicand. So this is just a fancy way of writing the 4th root of 81, which I believe last class we said was 3, because we went ahead and showed that 3 to the 4th equals 81. And so if the numerator is 1, we're just taking a radical. If the numerator, pardon me, and the fractional exponent is 1, we're looking at a radical. Instead, if I go even more general, if I have x to the m over n, and if that fraction has a numerator other than 1, again, because it's a fractional exponent, it tells me I'm going to have a radical. The base is going to be my radicand. Just like before, the denominator of the exponent is going to be my index. So I've written a lot. Fractional exponent, I'm drawing a radical. The base is the radicand. The denominator is the index. But the numerator of the exponent becomes an exponent. And so we're going to take the nth root of x and raise it to the m. And I apologize, I wrote those things too close together. I'm going to rewrite that down here. X to the m over n is going to be the nth root of x raised to the m power. And we can write it that way, or that's going to be equivalent to the nth root of x to the m power. And the way in which you treat it can vary, depending on arithmetic-wise, what's easier for you. For example, if I have something like, let's say, 36 to the 3/2. Well, for that, I have two options. One option, I have a fractional exponent. I need a radical. My radicand is 36. The denominator is 2, so I'm taking the second root, which is my square root. The numerator is 3, so I'll cube it. And writing it this way, the square root of 36 is 6, and then 6 to the third is 216. The other way, I could write that as the square root of 36 cubed, but I'm going to apologize. I'm not going to try to cube 36 in my head. When I take 36 and raise it to the third power, I get something crazy like 46,656. But then I have to go through and take the square root of that, which is 216. But for this one, I think that top way, taking the square root first and then cubing it, is a little bit less intimidating. But you see that both ways take me to the same result. So let's look at another example. Let's look at, let's say I have 32 to the 2/5 power. Again, because that exponent is a fraction, it means I'm going to have a radical. My radicand is going to be based around 32. The denominator is the index, and the numerator becomes an exponent. And so now the 5th root of 32 we saw previously is 2. And so I'm going to square 2 and say that my end result is 4. You guys are being really quiet. I hope it means you're listening. Thoughts? How's this look?
Pretty good.
Okay. It's an important life skill to be able to go from this expression with a fractional exponent to writing it in radical form. You need to be able to do that. I need to see that type of work. I want to see that type of work for any question with a fractional exponent. Is anybody interested in seeing how you can get that final answer from a calculator if you want to do a check or if you're doubting your number skills?
I would like
Yes.
Okay, so we're going to start with a calculator. I'm going to do it, well, no, this direction I'm going to do it, this one I'm going to do in just the same way for pretty much any brand. I'm going to start with 32, and then we're raising it to a power. So I'm going to use my caret up button. Now, in order to do this, you need to make peace with the parentheses key on your calculator, because that exponent is a fraction, the whole fraction. So you want to open a set of parentheses. Then you want to enter the fraction 2/5. If you're good with a fraction on your button on your calculator, you can use that. I have a tendency to use division to put in my fraction, so I'll type in 2 divided by 5. Then I'm going to close my parentheses. And as you look at your calculator, if you type that in, 32 caret up parentheses 2 divided by 5, it almost looks like that 32 to the 2/5. And so when you hit your equal key, you get that 4. Could everybody get that one from your calculator?
Yes.
Okay, so if you're concerned with the arithmetic, the number of it, If you need to use the calculator to do the computation, that's fine. But again, remember, in order to get full credit, I don't want to just know you know what buttons to push, but I want to know that you know how to rewrite that as a radical expression. So I expect you to rewrite that as a radical expression before you evaluate. So let's have you folks do one. Let's say I have, what numbers have we used so far? Let's say I have 27 to the 2/3. I want to give you a minute to rewrite that as a radical and then evaluate it for me and tell me what you get. Did anybody get 9?
Yeah.
Where I have 27 to the 2/3. The denominator is 3, so I want the cube root of 27, which I'm going to square. The cube root of 27 is 3, and 3 squared is 9. But let's make these a little bit more fun. Let's look at a couple others. Next one I want to look at is a little bit different. What if I have 16 to the negative 5/4? There's a whole lot of things going on here. First of all, does everybody remember that if I have a negative exponent, it means I'm going to have a fraction. It means I'm going to take the reciprocal. It has nothing to do with the fact that the original exponent is a fraction. It means I'm going to take that expression with a negative exponent and write it as a fraction, 1 over that same quantity to the absolute value of the exponent, or a positive exponent. Then you have to realize that if you have a fraction in the exponent, it means you're going to have a radical expression. And so that radical is in the denominator. The radicand is going to be the power of 16. My index is going to be the 4. And then exponent, I'm going to raise that to the 5th power. Then the 4th root of 16 is 2. And 2 to the 5th is 32. And so my final answer would be that 16 to the negative 5/4 is equal to 1 over 32. I'd like everybody to take a minute and do that one with your calculator. With my calculator, I want to just type in 16, caret up, parentheses, negative 5/4. And when I do that with my calculator, 16 to the negative 5/4, I get a decimal, 0.03125. Does everybody else get that same decimal?
My calculator gave me the fraction.
Okay, all right. Then, your calculator must be set in some sort of mode where it gives you the answer as a fraction. What type of calculator are you using?
I got the TI 36X Pro, and it's got the degree symbol up top there in the top bar.
Okay, degrees would mean the way it measures angles. It's measuring angles in degrees and not
That's got nothing to do with it.
radians. No, that's another thing. But does your calculator have a button mode?
Button mode, where would I find that?
It says mode.
Oh yeah, up top, yeah, I got it.
Yeah, when you press mode,
Yep.
is there something in there that says fraction or something?
I got degree, rad, grad, norm, psi, English, float, real.
Okay. All right, but it's set in a mode to give you that fraction. Other people, did you guys get the decimal?
Mine got the decimal, yeah.
Yeah, I did too.
If you're doing this and you're using your calculator to evaluate it and it gives you a decimal, do you know how to change that decimal into a fraction?
I do, yeah.
Anybody need to be refreshed on that process?
Can you refresh it for me, please?
Okay. If you have a graphing calculator, do you have a graphing calculator?
Yes.
Okay, with the graphing calculator, where I have that 0.0321, I'm going to press the button on mine. It's third button down on the left. There's a button that says math.
Okay.
So with the grapher, you're going to go to math. And then on mine, choice one is arrow FRAC. So I'm going to just press enter and it changes it into a fraction.
Okay, thank you so much. Sorry about that.
Does anybody have the TI 30X that wants to change that 0.03125 into a fraction? Does
Yeah,
any-
please.
Okay, if you have a not graphing calculator, it's not too much harder. I'm looking at my calculator and you see the top left-hand button is a different color and it's called second. Below that button, there's a button that says log. That deals with logarithms. We're not going there. But next to the logarithm button, there's a button that says PRB. That deals with probability functions. Pardon me, we're not going there. What do you see written in the same color as your second button? Above the PRB button on the calculator, there's something that's double arrow D.
Yep, I see that.
That changes a fraction into a decimal or a decimal into a fraction. So what you're going to do with your decimal, you're going to press that second button and then you're going to press that PRB, which will give you that fraction to a decimal, and then you're going to press equals. And does that change it into the 1/32?
Let me try it again. Sorry. Yeah, I got it. Thank you.
Okay, and did you know that your calculator could turn not every fraction, but a lot of fractions into decimals for you, and decimals into fractions? It's a two-way street there, so.
Great.
Okay, so in terms of evaluating expressions, if it's just a number problem with a rational exponent, is everybody okay? If so, our rules for exponents hold true for rational exponents. So, for example, if I'm asked to simplify, and that's what I'll be asking you to do with each of the following. Let's say I have in parentheses 3x to the 2/3 times 4x to the 1/3. There's no need to rewrite this in terms of a radical first. We can just use our exponent rules. Does everybody remember that if I have the same base, in order to multiply, I add exponents? And so here, in order to find this product, first, I'm going to use my commutative and associative properties to say, well, I'm going to multiply the numbers by each other. Then I'm going to multiply the powers of x by each other. And I think that's pretty straightforward. Then the hard part, 3 times 4 is 12. But then here, when I multiply those, because they have the same base, don't I keep the base and add the exponents? And if I add 2/3 plus 1/3, does everybody remember adding fractions? If they have a common denominator, I'm keeping that denominator, and I'm adding the numerators. 2 plus 1 is 3. And so, well, 3/3 is just 1. And so that's just 12x to the first, or in simplest form, 12x. And so do you see, while this looks a lot scarier than those original exponent problems that we looked at in homework P2, if the exponents are fractions, they work in the same way. So let's look at another one. Let's say I want to simplify, and I've got 2y to the 1/5 raised to the 4th over y to the 3/10. Let's go ahead and work on this first with our exponent rules. And then very last step, if we need to, we'll write our answer in radical form. But again, if we can make use of those exponent rules first, it's going to make our lives easier. Does everybody remember that if I raise a product to a power, I raise each factor to the power? So that gives me 2 to the 4th, y to the 1/5 to the 4th. Right now, I'm not touching that denominator. I'm just going to leave it, bring it along. And then does everybody also remember, with exponential expressions, if I raise a power to a power, I multiply those exponents. So that gives me 2 to the 4th, y to the, well, if I take 1/5 times 4, doesn't that give me 4/5 over y to the 3/10? How's that look so far? Now, when I divide with a common base, I subtract exponents, so that would be y to the 4/5 minus 3/10. I'm kind of old school, so I'm going to do that subtraction by hand, just to remind you folks how to do that subtraction by hand. I guess if you need to, you could also use the calculator with the fraction key to evaluate that difference. But I'm going to go through and do it old school. Does everybody remember the common denominator here would be 10? That 3/10 already has that as a denominator, so I don't need to change it. That 4/5, in order to change 5 into 10, I multiply by 2. So I have to multiply the 4 by 2, giving me 8/10. We worked hard to get the common denominator, so we'll keep it. Subtracting the numerators, 8 minus 3 is 5. So that gives me 2 to the 4ths, y to the 5/10. But I'm guessing that each and every one of you remembers how to reduce that fraction 5/10. What does 5/10 reduce to?
1/2.
1/2. And so that gives me 2 to the 4th, y to the 1/2. Now let's see, 2 to the 4th is 2 times 2 times 2 times 2 would give me 16. And y to the 1/2 just means the square root of y. And so that would be my final answer in radical form. If they didn't ask for radical form, 16y to the 1/2 would be my simplified exponential form. How cool is that? That something that looks that interesting can simplify to 16 times the square root of y. Questions on that one?
So I have a little question. So when we first look at the problem, right? 2y to the 1/5 to the power of 4 divided by y to the 3/10. Now, what you're saying is it's not, you don't want to solve for parentheses first because you could already kind of take your y, not
For the
cube
1/5 and write it as
root
the
of
fifth root.
5. You know what I'm saying? You could do that first, couldn't you? But you're saying you don't want to do that?
I'm saying that 9 times out of 10, it's much easier to work with your exponent laws than it is to work with your radicals.
Okay. Because naturally, I just want to like do the parentheses first, but.
Well, inside the parentheses, we're multiplying. We've got a variable with the exponent. There's no real computation we can do there. And so on the outside, we have an exponent. Let's go ahead and use our exponent laws.
Okay.
Because after parentheses, the next thing is exponents.
Okay.
All right. And again, I think subtracting the exponents would be much easier if you took that other approach where I have 2y to the 1/5 to the 4th over y to the 3/10. You'd end up with 2 times the 5th root of y
Yeah.
to the 4th over the 10th root of y to the 3rd.
Oh, that looks pretty much more murky, doesn't it?
Yeah. The exponents are much easier to deal with. And that's why we spend a bit of time on those exponent laws, even though they're probably something you've seen before. And you're going to find this is sort of a life skill as you graduate from algebra to trig to pre-calc to calc. If you're following that path, you're going to find in calculus, if I have something like the 5th root of y, that's going to be a bear to work with. But instead, if I can change that into y to the 1/5, I've got all sorts of rules for exponents that are much easier to use. And so usually it's easier to manipulate exponents than it is to work with radicals. Does that make sense?
Yeah. Makes a lot more sense now that you actually wrote it out, and now I can see.
So, but let's look at another example. That's one that doesn't look like you'd want to initially turn it into a fractional exponent, but if you do, it makes your life a lot easier. What if you were asked to simplify the 9th root of x to the 6th? Well, if I were to change that into exponential notation, My base is x. I have a radical, so my exponent's going to be a fraction. The index is in the denominator. The exponent is in the numerator. With me so far? Let's
Yes.
look. Can anybody reduce that fraction 6/9?
2/3.
2/3. There's a common factor of 3. When we divide it out, we get x to the 2/3. And so that's the cube root of x squared. And if there were a number in there that we were substituting for x to evaluate that, doesn't that one look much simpler to work with?
Yes.
And so those, that ability to use your exponent laws, simplify fractions, sometimes it's much easier to work with those fractional exponents than it is to, to work with the radicals. Let's look at a couple more. Let's say I ask you to simplify using exponent laws. Let's say I have, let's look at in parentheses, 125 x to
Hello?
I think she might have lagged out.
Oh, okay.
Yeah, she froze for me. Okay, good thing it's not only me.
Yeah, I was
Yeah.
wondering the same
Same
thing.
here.
My internet's been kind of shoddy lately, so I thought it was me too.
I immediately went to like a browser and was like, shit, did my internet just go out?
Well, she told us to wait until like she would hop on, so I think we should just do that because like you never know if she's gonna hop back on.
Yeah, like, does she even notice? Like, she could
I'm
still.
gonna. Oh,
She said before she'll figure it out eventually.
she just did that.
Okay.
Oh no, this is not gonna be good. Hour goes by. Where's our teacher? Nowhere to be found.
hello? I
Hey there.
apologize.
Yes, welcome back.
Welcome
I'm on a
back.
different computer. I can't write on the screen of the Chromebook that I'm talking to you now. This is the first time this has happened this semester. It happened periodically last semester. The Surface overheated. And so I just need to give it like 2 minutes to cool down, and then I'll restart it and pick up in the middle of the problem that we're working on. I apologize if it happens. Thank you for not just ditching class and waiting for me. Guys, mind giving me 2 minutes for this other machine to cool down a little bit and restart it. And if it, because this is a 2-hour class, usually in between my 1-hour classes, I take a minute and put the computer to sleep in between times. If it happens repeatedly, we'll just have to take a 5-minute break in the middle of class. I'm sorry for that. So if you guys want to stretch your leg,
Okay, don't
2
worry about it.
see if I can get this other computer to start up again. Oh, there it goes. It's starting slowly but surely. And you'll know I'm in it again with the other computer when you start hearing the feedback from the 2 computers being next to each other. So. It used to only happen on super sunny days when my computer was, when the Surface was where the Chromebook is now on the desk and the sun would shine in on it. I don't know why it overheated right now because I didn't have it on too much before your class, but let's see what we can do.
How old is the computer? Because sometimes the age of the computer can define the like warranty or like the time.
Well, what it is I do not have touch screen computer. This is a Surface, one of those Surfaces that I borrowed from the college. And so I really
Gotcha.
have no idea how old it is. I know it's a college computer. I know the first couple of times that it happened, and I contacted them, they told me, just I have to let it cool down. Oh, I'm in it.
Oh my gosh, that's so scary.
Yeah. There, I left the meeting on the other computer. Let me reopen where we left off in the notes. Hopefully not too much of that was lost. And let me try that again. Let me reopen the notebook. There we go. Then let me go back to Zoom and share my screen. Oh, we did lose a little bit. Those couple examples, are you guys all right if I don't rewrite? Oh, actually, no, this was exactly where we left off, isn't it? Okay.
You might want to make sure you're recording now, maybe, too.
Okay, thank you.
Yeah.
And so
I think
looking
she
at
is
that,
on.
oh yeah, it's still recording. So if you guys were saying nasty things, well, I was.
No, we would never, never, not me.
Okay, all right. I think I had started trying to write 125 x to the 9th, y to the 6th to the 1/3. I'm going to shut up and ask you folks to simplify this one. And tell me what you got. Did you guys get what I got, or do you want me to hold off for a minute and give you a little bit more time?
I got what you got.
Okay, good. How about everybody else? Do we need to add details? I'm going to add details either way, but can I'm going to like fess up some of my own bad habits. In a classroom, when I give folks time to work on a problem, it's easy for me to be patient because I walk around the room and look over shoulders. I can't do that right now. So in order to make sure that I'm not too quick, I do silly things like check my email and the like while I'm waiting so that I give you guys enough time. And want to show you, I got the world's most adorable picture while I was waiting for you guys to do that problem. It's the newest photo of my grandson, but I digress. Okay, so as you raise a product to a power, you're going to raise each factor to that power. The number part, there's nothing to be done exponentially. And so I'm going to rewrite that as the cube root of 125, which brings me to 5. The variable part, when I raise a power to a power, I multiply exponents. So that gives me x to the 9/3, which reduces to 3. And here, when I multiply the exponents, I get y to the 6/3, which reduces to the 2nd. So hopefully these problems, I like to say the bark is worse than the bite. They aren't as difficult as they first look. At least I hope not for you guys. Let's look at one more. Let's go ahead and actually let's look at 2 more. First, let's ask you to simplify. And let's look at, oh, you know what? I take that back. We did that one already. Let's look at, okay, 20x to the 1/2 over 5x to the 1/4. So simplify it with your exponents first, and then write it in radical form. Have I waited long enough? Did anybody else get 4 times the 4th root of x?
I did, yeah.
So what we're doing is we're taking the 20 and dividing it by 5, which gives me the 4. And then with the variable, in order to divide, we're going to keep the base the same and subtract the exponents. 1/2 minus 1/4 is 1/4, which we can rewrite as a radical. And then lastly, let's just ask you to simplify. And I'm going to take the 12th root of x to the 4th, y to the 8th. Ready yet? Did anybody else get the cube root of the product x, y squared?
No, could you show examples, please?
Sure. So we've got x to the 4th, y to the 8th. And because I'm taking the 12th root, I can think of that, raising that to the 1/12th power. So far, so good? Then when I raise this product to that power, I raise each factor to that power. And when I raise a power to a power, I multiply exponents. So that gives me x to the 4/12, y to the 8/12. So far, so good?
Yep.
4/12 reduces to 1/3. 8/12 reduces to 2/3. So I've got the cube root of x times the cube root of y squared, which would give me the cube root of xy squared. Better?
Yeah, thank you.
There's a technicality. I don't think I assigned any in my labs that involve this technicality, but is everybody all right going back to the original problem? No matter what type of number x is, whether it's positive or negative, x to the fourth would make it positive. And so technically, we should put absolute values around that x to acknowledge the fact that whether x was positive or negative, because I squared it, it will, make that end result, because I raised it to the fourth power, pardon me, it'll make that end result positive. I think all of the ones that I assigned assumed that x and y are non-negative. And if we're starting with that assumption that they're non-negative, that means that we don't have to worry about throwing that absolute value in there. Again, it's a technicality. In this class, you're not going to really have to worry about throwing that absolute value in there. But in future classes, realize that if you see somebody put an absolute value bar around it, they're being very rigorous and saying, okay, even if x were a negative number, I know that this end result will be positive because I was raising it to an even power. Okay. There are plenty of those for you to practice in the rest of that homework. P3, I think last class, we said that 1 through 19 involves simplifying radicals and rationalizing the denominator. It's the ones after that that involve the fractional exponents. That's why this homework is due after the quiz, because the fractional exponents are not on the quiz, but the questions on 1 through 19 that involve simplifying radicals and rationalizing the denominator, that will be on the quiz this weekend. All right. And rather than doing a whole bunch more together, I'm going to ask that you folks work on those on your homework over the weekend. And if there are still problems, we will deal with those on Tuesday morning. But we're going to change gears a little bit. And I know the people in the Monday, Wednesday, Friday section were happy to see where we're going next, because where we're going next, I think it might be a little bit more familiar territory for most of you than those fractional exponents. Although I guess I do want to ask, have any of you seen fractions and exponents before this?
Yes.
Very little.
A very little bit. Is this first time for anybody, or is this all something you might have seen once and just don't remember?
I don't remember any of this, no.
Okay. All right. Did we go through it slowly enough for you to kind of wrap your mind around it a little bit?
Oh yeah, this is a lot. It's more like slower and more nicer, I think.
Okay. All right. Because my fear is, I know that a lot of what we're doing could be a review for people who took like a more than one algebra class in high school. But I know there's some people that it's been a long time. And I also know that there's some people who only took one algebra class in high school and didn't get all of this. So I'm always worried, am I going too fast? Am I going too slow? So, okay. Next section is section P4, and P4 deals with polynomials. And if anybody's interested, This chapter is chapter P because it's considered preliminary information. It's kind of like background stuff. Before we start looking at polynomials, we have a couple of definitions that we need to go over. Some of them I know they're expressions that we've been using already, but let's make sure we've got official definitions. The first is that of a term. And a term is defined as the product of constants, and variables. Help. What operation gives me a product?
Multiplication.
So this means that we're multiplying. Does everybody remember constants don't change? They're your numbers. And variables, most people think of as letters. And so some examples of terms might be 3x, might be 4xy, might be 15x to the third, and might be x squared y to the fifth. As I go on to the next thing that I'm writing, I want to leave a couple lines here because I do want to write some information below each of those. Before we do that, one thing we have to clarify, if I'm talking about something that's a polynomial, in a polynomial, the exponents on the variables have to be whole numbers. So with polynomials, we're not going to worry too much about those fractional exponents. We talk about a coefficient. And I'm guessing that everybody's heard that word coefficient before. I think we've been using it already. Can anybody remember what a coefficient is?
Remember it as the number before a variable.
The
Like
number
when you're
before the
multiplying.
variable, or are you all right if I call that the constant factor of a term?
Yeah.
So underneath each of these, I'd like to write what the coefficient is. And so on 3x, the coefficient would be 3. On 4xy, the coefficient would be 4. What's the coefficient on 15x to the third?
15.
Beautiful. Last one's, well, actually, would it hurt anybody's feelings if I added one more after the x squared y to the fifth? Does everybody have room to add one more here? I'm going to add just 7. But now over here on the x squared y to the fifth, what would you tell me the coefficient is?
1.
1. And does everybody remember if there's no coefficient written? It's 1. And on 7, the coefficient would be 7. Another thing you need to be able to look at in a term is to talk about the degree of a term. And can anybody remember from a past life what we refer to when we talk about the degree of a term? The degree refers to the exponent. If there's one variable, it's just that exponent. If there's more than one variable, it's the sum of the exponents on the variables. And so on that other line that I left, I'd like to find the degree of each of those terms. On 3x, the variable is x. There's only one variable. What's the exponent on that x?
Just one.
Just one. So we'll say that that's first degree. Now over here, I have two variables. I have an x with an exponent of 1. I have a y with an exponent of 1. So the degree would be 1 plus 1, or we'd say that's second degree. On the 15, x to the third, there's only one variable. Its exponent is 3. So is everybody all right? That would be third degree. What would be the degree of x squared y to the 5th? My exponents are 2 and 5, so when I add them, I get 7, so that's considered 7th degree. Now, the plain old 7 has no variable part. If there is no variable part, can't I think of that 7 as being 7 times x to the 0? And so if I have a constant, a plain old number, the degree of the constant term is 0. So let's spell that out a little bit. We refer to the constant term if it has no variable. Constant is the coefficient. And for any constant term, the degree is 0. So again, for example, does anybody have a favorite number? Nobody's helping me out here. Okay, let's say 13. For 13, the coefficient would be 13. And because there is no variable part, the degree would be 0. So far, so good.
Yes.
All right. Then I'm going to turn the page and add a little bit to what we're talking about. Next definition is a polynomial. And the prefix poly means many. So a polynomial is the sum of many terms. An example of a polynomial might be something like x squared minus 3x cubed plus 4x to the 5th minus 2. As I look at this polynomial, does everybody see that in this example, my polynomial has 1, 2, 3, 4 terms? There are 4 things that are being added or subtracted. In the homework, you're going to find some polynomials that they ask you to write in descending order. And if something's descending, it's going down. When we talk about descending order, what we want to go down or decrease are the exponents. So something's in descending order if the exponents decrease, not decrease, sorry about that. As you go from left to right. And so if I want to put this polynomial, pardon me, into descending order, my highest exponent is 5. So I'll start with that 4x to the 5th. There's a plus sign there, so that's positive. My next exponent is 3, my next highest exponent. So that gives me 3x cubed. I'm going to think of that as being a -3, so the negative sign will stick with the 3. My next highest exponent is 2, my x squared. That's positive, so we'll put a plus here. And then my lowest exponent is 0, and so that -2 will be last. When we have a polynomial, we sometimes talk about the leading coefficient. If something's in the lead, it means it's coming first. And so my leading coefficient is going to be my first coefficient. But it's only going to be the first one after it's in descending order. So we'll say that it's the coefficient on the highest degree term. And so in the example up above, we'll say that the leading coefficient is 4. So technically, it's not always the one that's written first. You've got to put it in descending order before you reach that executive decision. Next, we talk about the degree of a polynomial. When I talk about the degree of the entire polynomial.
Oh my God, this is so fucking boring.
I'm sorry. We just got to make sure everybody's on the same page definition wise. The degree of the polynomial is the degree of the highest degree term. And so this polynomial would be a 5th degree polynomial. And so again, I apologize if it's boring, but you're going to see questions in the homework that give you something like 9x squared plus 6x minus 5x to the 6th plus 2, and they ask you to put it in descending order. Find the leading coefficient, the degree of the polynomial, and the constant term. And so I'm going to shut up for just a minute and ask you to do all of that for me. Descending order would be -5x to the 6th plus 9x squared plus 6x plus 2. How'd you guys do? My exponents are going down. Leading coefficient, now that it's in order, the first coefficient is -5. Degree, on that leading term, the highest exponent is 6, so it's 6th degree. And the constant term, the plain old number, is 2. One more. What if I have 2x to the 1/2 plus 3x to the -1 plus 5? And this one's a trick question. Do you remember we had said at the beginning that it's only a polynomial if the exponents are whole numbers? Because we have a negative exponent and because we have a rational exponent, a fraction, we're going to say that this one's not a polynomial. And so we're not going to deal with it in that way. So when you look at these in the homework, there's going to be a radio button. Is it a polynomial or not? And then if it is a polynomial, put it in descending order. What's the leading coefficient? What's the degree? What's the constant term? We good?
So would we ever have a question that one of the exponents is a whole number and another isn't?
You could, but if one of them's not a whole number, then it's not a polynomial. It's a different type of equation.
And then we would
Not a
never,
whole number. We've got something involving either fractions or radicals, and we don't consider those polynomials. At least Mr. Blitzer doesn't at this stage of the game. So it would be not a polynomial or beyond the scope of the course. Okay,
got it. Thank you.
all right. So then when we look at polynomials, we classify polynomials by the number of terms. And again, if this is something you've seen before, I don't mean to be insulting, but just in case some people aren't familiar with the terminology. First classification, we might look at a monomial. And mono means one. So a monomial has one term. So an example might be something like 15x squared y z cubed. Lots of variables in there, but it's all multiplication. It's a single term. Instead of binomial, what does that prefix bi tell me? You guys aren't helping. Two terms. So an example might be something like we were looking at when discussing conjugate pairs, a squared, actually, let me change that. A squared minus b squared. I've got two terms. Trinomial.
Three.
Beautiful. Three terms. And I might have something like x squared plus 2x plus 1. And we're going to find that we're going to be doing a lot of things with trinomials, especially in that next section when we start factoring. Sometimes you see an expression for a general polynomial in one variable. And so if it's in one variable and I want to leave it general, I don't want to give specific exponents. So if my variable is x, I'll start with x to the n, and then I'm going to leave a space here. The next exponent will go down 1, x to the n minus 1. The next exponent will go down again, x to the n minus 2. And they'll keep going down until I just have something times x to the first, and then I'll have a constant term. And leaving it general, we want to have all of these have a potential coefficient. For those coefficients, I'm going to have them all be a. And they'll be subscripted. A sub n is a coefficient on x to the n, a sub n minus 1, a sub n minus 2. This would be a sub 1, and this last one would be a sub 0. And so if you see an expression like that, that's just generalizing. General polynomial can be of any size. And now that we've defined polynomials and different classifications, the next thing that we look at, and I think I'm going to turn a page so we have a little bit more room. Oh no, let's just at this one part down here. We're going to start looking at doing operations on polynomials. And the first operation that we're going to look at is addition. And in order to add polynomials, is something that we've talked about already. We're going to combine like terms. So looking at a couple of examples, if I have 3x squared plus 4x squared, what would I get?
Seven x squared.
Beautiful. What if instead I have something like negative 7x cubed plus 6x squared minus 11x plus 3, and I want to add to that 19x cubed minus 11x squared plus 7x minus 17. Is everybody all right? While those are in parentheses, I can't do anything inside the parentheses. So I can almost think of the parentheses as each having a coefficient of 1 and just lift the parentheses by multiplying by 1. And then we'd want to match up our like terms. Negative 7x cubed, positive 19x cubed. Well, they're both x cubed, and negative 7 plus 19 would be 12. 6x squared minus 11x squared, they're both x squared. Positive 6 minus 11 would be negative 5. Minus 11x plus 7x, they're both like terms, they both have an x. Negative 11 plus 7 is negative 4. And then lastly, the constant terms, 3 minus 17 would be negative 14. Is that all right for everybody?
Yeah, that's okay.
One more, let's look at negative 2x squared y plus xy squared. And I want to add to that 4yx squared plus 7xy squared plus 2xy. I'm guessing that everybody can look at this and recognize that xy squared, those are like terms. 1 plus 7 would be 8. I'm more concerned with here, the negative 2x squared y and the 4yx squared. Does everybody recognize that those two are like terms? It's multiplication, which is commutative, but the same variables have the same exponents on them. So I can add those two, giving me 2. I'm going to write it as x squared y. You could write it as 2yx squared if you want it. But it's most normal to put your variables in alphabetical order. And then here, that last term is not like with any of them, so it comes along with that. So adding polynomials, combining like terms, I think that's something that we've discussed already. Is that a life skill you all have? I'm guessing that means yes, because nobody yelled at me. So then after we add, the next thing that we want to do is subtract. Polynomials. And again, I think the idea behind subtracting polynomials is something that we talked about a little bit in the beginning when we were simplifying expressions. What we have to do to subtract is add the opposite. And so in practice, what that means is behind the subtraction. We're going to distribute -1 to the polynomial and then add. Just a couple examples of these. If I have x plus 2 in parentheses, minus in parentheses 3x minus 5, I'm going to rewrite this to show the work. X plus 2 in parentheses minus 3x minus 5. I'm going to change that into -1. And I'm going to take that -1 and distribute. So that's going to make it minus 3x plus 5. But again, I'm adding those to that front polynomial. I think on that one quiz, there were some people who didn't treat that next step now as all addition. And so x plus -3x is -2x, 2 plus 5 is 7. So one more. I'm going to ask you folks to do 18x to the 4th minus 2x to the 3rd minus 7x plus 8. That's my first polynomial. And from that, I want to subtract 9x to the 4th minus 6x to the 3rd minus 5x squared plus 7. And I'm going to be quiet and give you folks a minute to do this. Did everybody else get, oops, miswrote, 9x to the 4th plus 4x to the 3rd minus 5x squared minus 7x plus 1. Does anybody want me to add detail?
I got
No, I got that.
positive 5x squared.
Thank you. Plus 5x.
That was okay.
Yeah, it's a typo on my part.
Okay, thank you.
Does anybody need detail or is that one all right?
I'm good.
Okay. Then if we're pros at adding and subtracting, the next place that we're going to go is multiplying polynomials. And when we multiply polynomials, what we do depends upon the size of the polynomial. First case, if I'm looking at multiplying a monomial by a monomial, well, this is something that we've done already. We multiply the coefficients and we use our exponent rules on the variables. And I think that's a skill that's everybody's master. So I'm going to look at 6xy to the fourth times 12x to the third y to the second. And when you go ahead and multiply that, then we're going to multiply the coefficients, 6 times 12, which will give me 72. On the variables with the same base, I'm going to add the exponents. So x to the 1 plus 3 would give me x to the fourth. And on the y's, base of y, I have y to the fourth times y to the second. So adding those exponents, 4 plus 2 would give me y to the sixth. Is that a skill that everybody's comfortable with?
Yeah.
Great. Then let's look at multiplying a monomial by a polynomial. And again, I think this is something that you're familiar with. The word of the day is the big D distribute. And so, for example, if I have 8x times x squared plus 3x minus 4, again, I'm going to add an extra step in between that you don't necessarily have to show, but just to make sure we're all on the same page. When I distribute, I need to take that 8x and multiply it by the x squared. Then I need to add that 8x times the 3x. And then because there's a minus sign, I need to subtract that 8x times 4, giving me 8x cubed plus 24x squared minus 32x. I hope you're all on the same page with that one, but let's make sure. Let's have you folks multiply negative 2xy squared times x minus 2y plus 7. And tell me what you get. Did everybody get negative 2x squared y squared plus 4xy cubed minus 14xy squared? Distributed. Great.
I did.
Then, next product is something that we're going to focus on. We're going to see a lot. There's a couple of different ways, different approaches that I've seen. I want to go over all three of them so that we're within everybody's comfort zone. Next products that we look at are when we take a binomial times a binomial. And so that might be something like A plus B times A plus D. I'm sorry, C plus D. Let's put a C in there. I apologize. One method is doing repeated distribution. And so I'm going to take that A and multiply it by the C plus D. Then I'm going to add to it B times the C plus D. So we're distributing the C plus D over the first. And then I'm going to distribute again, giving me AC plus AD plus BC plus BD. And I think that there was a point in time somewhere in the 2000s where that was the way to go, because it's based on something that everybody's familiar with, the distributed property. We're using it twice. Next method, I believe I heard somebody refer to previously. Has anybody ever heard of FOIL? When I look at FOIL, F stands for first, O stands for outer, I stands for inner, L stands for last. And so when I look at A plus B times C plus D, when I talk about the first, I mean the first one in each parentheses. So that's AC. When I talk about the outer are the two extremes, the furthest to the right and the furthest to the left. And so the outer would be AD. When I talk about the inner, by the inner, I mean the middle two. So the two in the middle would be B times C. And when I talk about the last is the last one in each binomial. And so that would give me BD. And so it gives us the same results as that repeated distribution, but it's a memory aid to help us, rather than writing the distribution twice, first two, outer, inner, last. Is anybody in the room familiar with FOIL as opposed to distributing?
Yeah, I'm familiar with FOIL.
And then that FOIL became a bad thing because you have to memorize a word, and people wanted to really totally distance themselves from memorization at some point in time. Oh, probably in the mid-90s. But then there's another way of doing it. That's a box method. And honestly, this box method is something that I show in my math for early education majors, because it's kind of a way of getting elementary kids to wrap their minds around it. I'm going to draw a rectangle and have one dimension A plus B, and have the other dimension C plus D. And I can think of it as having, this has length A, this has length B, this has length C, this has length D. And I want to find the area of each little square. So this one would be A times C. This one would be B times C. This one would be A times D. And this one would be B times D. And so that would give me that same result, AC plus AD plus BC plus BD. And you notice they all take us to the same place. Is there anybody in the room that draws a little box whenever you multiply two binomials? I know every semester I have several students that use that box method. Is that familiar territory to any of you?
Would all the methods be okay on a test, like if you chose one over the other?
Yes. The reason that I'm showing you all three is because I'm not going to force you to use one way or another. I know that some people had this repeated distribution drilled into their heads in their formative years. And if that's within your comfort zone, by all means do that. Some people learned FOIL. If you've been FOILing all your life, go for it. When I do examples, I'm most likely to FOIL because way back when I learned algebra the first time, FOIL was the way they taught it. I also know that some people, neither of those kind of like ring a bell, but they've drawn the box every time. And if I let them draw the box, they'll get it right. So if you're a box method, by all means do it. They're all mathematically justifiable and they all take you to the same place. So I don't care which one you use, just get proficient at the one of your choice so that you make sure you get the same products with all of them.
Okay, thank you.
So next example, if I ask you, first example, if I ask you to take x plus 8 times x plus 5. Again, I'm kind of old dog, new tricks, so I like FOIL. So I'm going to do this one, FOIL first. The first in each x times x is x squared. Outer, the outside edges gives me 5x. Inner, when I multiply the middle two, I get 8x. Last, when I multiply the last in each binomial, I get 40. So that would give me x squared plus 13x plus 40. Again, if you wanted to distribute twice, it should take you to the same place. And if you drew the box, it would take you to the same place. Could everybody get that answer? Oh, geez. And I'm looking at the clock and realizing that I thought we had about 15 minutes left and we've gone a minute over. So I'm going to stop here. And let's see. I apologize for talking too long. I'm going to stop recording.